Continuing with section 2.1, we now look at matrix multiplication. Now, we cannot multiply all two matrices of any size. There is some restriction, and that is that if I want to find the product AB, then the order of A and B has to satisfy certain condition. So if A is of order M by P and B is of order P by N, then I can multiply or I can get this product A, B. And what we are looking for is that the number of rows of B should be same as number of columns of A. So we are basically looking at these two numbers. So when you write the matrices side by side, the two matrices that you are multiplying, then the number of columns of the matrix which is on the left must be equal to the number of rows of the matrix which is on the right. Then only we can multiply the matrices. And the resulting matrix, let's say, call it a C matrix. So let's say AB gives us the matrix C. Then the size of the matrix C will be M by N. So whatever is left here, that's how the matrices can be multiplied. Now, the way we can think of matrices multiplication is, if you recall, if we think of the matrices as in vector notation, so A matrix consists of P vectors, each of size M, and then when in B, the vectors, there are N vectors and each of size P. So the way we multiply AB is that we multiply we multiply the whole matrix basically with the each vector of each column vector in B. So, and one by one. So there are so when we multiply AB, we kind of get a vector. First vector of the product is the A matrix multiplied by the B. So this is the dot product which is happening between the row vectors and column vectors. So we have choose row vectors of A. So for example, if A has 1, 1, 1, 2, 1, 3, A2, 1, A2, 2, A2, 3. Now this is the size of this is 2 by 3. So the B matrix must have a size 3 by something. So let's choose it at 3 by 2. So then we can say it is B11, B12, C, B21, B22, and B31, B33. Then the resulting matrix, you can see, it will be of size 2 by 2. So we can say this will be equal to C11, C12, C21, C22, where Cij, I can define Cij, or we can do each of them. There are only 4 of them. Where C11 will be equal to the row 1 of A, which means A11, A12, A13 times. Okay, I didn't leave enough space here. Okay, to rewrite it. Maybe I should go here, yeah. So the C11 will be equal to A11, A12, A13 times B11, B12, B13. sorry, B12, B21, B31, because these are the rows are changing. So B21, B31. So we take the dot product. So it will be A11, B211 plus A12, B21 plus A13, B31. So this is giving us one entry, the entry which goes in the place C11. So notice here these indices of C tell you which row to pick and which column to pick. But the row matrix will be on the left and the column matrix will be on the right. So for example, when we are trying to find the C21, it means now the second row of A. So A21, A22, A23. And it is being multiplied by the first column of B. So B11, B21, and B31. So same way, now you have to do the dot product. So A21, B11 plus A22, B21 plus A23, B31, and so on. So this is how you multiply matrices. Now, if we are multiplying a matrix by a single vector, then it will look like this. It is something that we have seen before as a vector equation. So let's look at the properties of matrices, and then again we can show some proofs here. And it says let A be an m by n matrix and let B and C have sizes for which the indicated sums and products are defined. Then AB into C is the same as A into BC. So it's saying multiplying the three matrices means you multiply two of them first and then multiply the answer with the third. So if I multiply A to B first and then multiply the answer with the C, it's the same thing as if I had multiplied BC first and then multiply with A. But note here, the very important thing is you cannot change the order of the matrices. So if you multiply by BC first, you cannot put the A here. That will not be correct because matrices do not obey commutative property under multiplication. So that's why we do not have a condition like this here, because this is not, they are not equal. It's given down here. So this will be wrong. A has to be on this side. So again, this is now these two are B and C are what we call the distributive property among matrices. So again, we have to obey the order here. So when we say A times B plus C, so when we bring the A in, when we distribute the A, it has to stay on the left. So when you have A times B plus C, it will distribute like the product will be AB plus AC. You cannot change the order. Okay. Now when we multiply a product of matrices by a scalar, it gives us the same result as if we multiply one of the matrices by that scalar first and then take the product with the other matrix. That's what is being said in D. And in E it says that IM, the identity matrix of size M into A, will give us A. Note that because identity matrix should work from both sides, but the problem with the different size not square matrices is that if you have an identity matrix here, you cannot just simply write this for if A is not a square matrix, because if A is of order m by n, then this matrix I must be such that the number of columns meet is equal to n. But since identity matrix is a square matrix, so it means this should be of order. So I have to take the m by n as the order of A. So this I should have the order m. It should be im. And when I multiply the matrix from the right, it should match the number n. So it should be of order n. But both ways we get A. But if A is a square matrix, then we can just simply write A is equal to AI is equal to A. Now, the cancellation laws do not hold for matrix multiplication. What does that mean? It means if you have A, B is equal to AC, like the product of A and B is the same as product of A and C, you cannot say that B is equal to C. In other words, you cannot just cancel this A, or you cannot divide by A. And also, the zero property, if you recall, we say that if two numbers are being multiplied and the product is 0, then one of them has to be 0. So in matrices, if you multiply two matrices and the answer you are getting is a 0 matrix, that does not mean that one of them has to be 0. It means both of them could be non-zero. So in matrices, you cannot assume things. Okay, the next thing is the transpose of a matrix. Before that, powers of a matrix. Now, if we are talking about A squared, now A is an m by n matrix. N by n matrix, it has to be a square matrix in order to discuss powers, because if it is not a square matrix, you cannot multiply that. Because if A is of order m by n, then the next is of order m by n. So these two don't match, so you cannot multiply. So for a square matrices, A and B matrices. So if we have A and B matrices whose sizes are appropriate for the following sums and products, then A transpose of A transpose is equal to A. I believe we discussed what is A transpose. A transpose is basically the matrix that you obtain by swapping the rows and the columns. So this becomes A, looks like AJI. So the rows become the columns and the columns become the rows. But it's of order n by n. So this we cannot multiply. So A has to be order m by m or n by n. So we are taking it, well, we are not mentioning here what the size is, but you have to keep that in mind. It's a square matrix. It doesn't have to be square matrix, does it? No, I don't think so. Yeah, it may not be a square matrix, right? But for the product, I was talking about the product here. So here we have to have A is a square matrix. Here we are saying it's of order n by n, but here in this case we don't need a square matrix, so we are okay with a matrix of any size, and the transpose of A means the columns and the rows switch. So for example, if you have A is equal to A12, A13, A21, A22, A23, this is your A, then A transpose will be now of order 3 by 2. So it will become A11, A12, A13. So what happened, this row became the first column, and the second row becomes the second column. Okay, and we are saying here that the transpose of a transpose matrix of A will be equal to the matrix A, which makes sense because what happens in we have a matrix A and we take a transpose so that the columns become the row and the rows become the column. Now if we transpose it again, so it will go back to the previous position. The rows will become the columns of this will become the rows of A transpose. So this will be A11, the first column becomes the first row, and the second column becomes the second row, which is back as to A. Then if you have A plus B transpose, then that is equal to A transpose plus B transpose. And you can see it for like a small matrix on your own. And then RA, so a matrix multiplied by a scalar, and if you are taking a transpose of that, it will be the same as R times the transpose matrix A. Now, A times B transpose is not A transpose times B transpose. The order now switches. So it is saying A times B transpose is equal to B transpose times A transpose. Okay, and then we had in that extra lecture, which I called SWAM. Okay. So there was this that if A transpose is equal to A is called a skew matrix. Oh, sorry, it's called a symmetric matrix. And if A transpose gives you negative A, then A is called a skew symmetric. And then we have to prove results. Okay, so show that this is symmetric, and B was show that okay, so how do we prove them? So you can give it a name, the first one, or whatever, but basically what we have to do is start with by taking the transpose of the matrix. So let's call it B. Okay, so we start by taking the transpose of B, which means the transpose of this one. And from the properties of transpose, remember when we had R, we have a transpose of R of times a matrix it is the same thing as R times the transpose of the matrix. So it means this 1/2 we can pull out, and we are left with 1/2 times A plus A transpose whole transpose. And then by the properties again, the second property here, the sum of two matrices transpose is the sum of the transpose of the two matrices. So this can be now written as 1/2 A transpose. Okay, maybe I should write it like this. 1/2. This transpose goes on this one and as well as on this one. So I get A transpose plus A transpose transpose. But we, again, from the previous properties, the transpose of a transpose gives us A, the first one there. So this one here is the A. So we end up getting this result is equal to 1/2 A transpose plus A, which is the same thing as we know from before. So which is the same thing as B. So it means B matrix, which is equal to this is symmetric. Therefore, or hence, A 1/2 times A plus A transpose is symmetric. In the same way now, we can prove the proof of B. You can call it a C matrix. So I will leave the proof for you guys to try, because it's very similar. Just you have to start by taking the C transpose and work it like I have shown, and then what we need to show is that the result is going to be negative of C. Then we say it is skew symmetric. Okay, now next video will be of section 2.2.